Okay, what we're looking at today is we are looking at the concept of internal resistance. Now, this is a topic that a lot of people say they get confused over, but just accept that this is actually very simple and then it will look a lot less confusing. So if we initially think about just some of the words that we're going to be using and double checking some of the equations, we'll look at that first. So firstly, I'd like you to think about EMF, or the electromotive force. What this is it's the work that's being done on a charge. It is the energy that's being transferred to those individual charges. Voltage, on the other hand, or potential difference, this is the work done by a charge. So the charge has been given energy by a power supply or an EMF source. It then goes around the circuit and does work on the components, transferring energy to them. Okay, so energy is transferred from one energy store, say the chemical energy store in a battery, to the charges. So the energy is going from a store to the electrical pathway. Then it is going through a potential difference, and the charges are transferring that energy from the electrical pathway to a different energy store. Okay, so that's that. A key equation that you need to remember is Ohm's law, so that the voltage is equal to the current multiplied by the resistance. So V is equal to I times R. And the other one is Kirchhoff's second law, that V total, so the total voltage, is equal to V1 plus V2 plus V3 plus etc. for a series circuit. Okay, so if there is a total amount of energy that is being provided to the circuit, that'll be split up across the different components. So we could say V total, or the EMF. So the work done on the charges, so the energy transferred to the charges, is going to be equal to the energy transferred to each of the components. So if we look at an electrical circuit, so I'll quickly draw one now. So we're going to have a 6-volt battery there. Going to have a resistor. We'll have an ammeter, and we'll connect that up. And then if we connect a voltmeter across our battery, the only thing this is not going to read is 6 volts or higher. It will only ever record something lower than 6 volts, say 5.8 volts. Because what this is recording is it is recording the difference in potential energy between this point and that point. It's saying, what is the difference between these two things? And it is called the terminal potential difference. So it's the terminal potential difference. It's saying, what's the difference in potential energy between this point and that point? So where's that missing voltage? Where's that missing energy gone? Well, if you've ever held a power supply or a battery while it's on, it's got warm. Okay? It has expended energy within itself. This is because, actually, batteries themselves, or power supplies, have a resistance. They have an internal resistance. Energy is being transferred from one store to another, and some of it is being expended, say, as thermal energy within the battery. So actually, we could redraw this like this. We could say, well, we've got a perfect cell with no resistance, but there is also a small resistor in there, which we'll call R. so small r, and this combined is actually what a battery is, or a cell. So this is the cell in total. So although the EMF, the energy being provided by this, is 6 volts, some of that energy is being expended in the resistor small r. Okay, so if we again complete this circuit, so we've got our resistor big R, and we have an ammeter to measure the current, we could say that V total, also known as the EMF, which has a symbol of epsilon, so the V total, or the EMF, is going to be equal to the voltage across the component plus the voltage expended in the battery, because we got that earlier from Kirchhoff's second law. Okay, so if we substitute in Ohm's law into this, we find that the EMF is equal to IR, or V1, because V equals I times R, plus I small r. That's the second component, that's the voltage drop across the battery, and that's the current, which will be the same everywhere in the circuit, multiplied by the resistance within the cell. And we can rearrange this one more time, literally just by bringing I outside the brackets. We end up with our equation like this. The EMF, or the total energy that's being transferred into the circuit, the work done on those charges, is equal to the current multiplied by the total resistance of the components plus the resistance of the internal resistor. We can look at this experimentally. So if I draw on my axes the terminal PD, so that's going to be, if we connect a voltmeter up across the two terminals, so across the battery, what would we read? And we measure the current in the circuit, we could find a value for this. So we can just measure the terminal PD and the current in the circuit. We could change the total current in the circuit by changing the total resistance in the circuit. And if we increase the resistance, we're going to decrease the current. So if we're to move along this axis, we are increasing big R, so that's the component resistance. And if we were to plot this, we would find that as the current increased, we would find that the terminal PD would decrease because more energy would be being transferred to that internal resistor. Because if we think about it, that is equal to IR plus I small r. So the bigger the current, the bigger impact this component is going to have. But if we increase the resistance, we're going to decrease the current, which is going to decrease the amount of energy that's being supplied to the internal resistor. And if we plotted those together, we would get a straight line where the gradient would be equal to minus R. So that's minus the internal resistance value. If we project this back, we'll get to a point where there is equivalent of 0 resistance within that battery, that cell, and so we'll have reached the peak EMF. This isn't possible because if there is 0 current, you won't be able to get any readings within that circuit. So this is a theoretical maximum output.